Exercise 4.29. Show that R2 minus the origin in the standard topology is homeomorphic to S1 times R. Circle times the line. Okay, well, before we try and actually write down homeomorphism of function between these two, let's try and understand why these are basically the same shape. Okay. Here's R2 minus the origin. It's known as the punctured plane because take the plane and you sort of puncture it at one point, you remove 1 point from it. And, well, to sort of end up with S1 cross R, which is sort of this infinite cylinder that goes up and down forever, we could sort of pull in every direction at this point and open it up a little bit to get this sort of circle, and then sort of push the rest of it down a bit so that we have almost looks like a volcano. Sort of goes down forever in each direction, and it's missing this top edge, right? And all right, well, if we sort of keep pulling in all this stuff down here, you can see how you might get a cylinder from this that would go on forever in the downward direction. Only trouble is it sort of stops at this missing edge. But maybe we can somehow sort of take the part of the surface up near the edge and sort of stretch it out infinitely much so that it will head all the way up there. Okay, so that this point that was missing before sort of ends up way up there at infinity. All right, that's one way to think about it. The idea behind this is basically the idea of polar coordinates. Okay, so you see each sort of ray I've drawn here corresponds to a fixed angle about the origin, and then those end up being these rays and then these vertical lines. Okay, and each vertical line is sort of all the points corresponding to a particular point on S1, right, which basically is an angle. So S1 is recording sort of the angle of the points in the punctured plane, and then R sort of tells you where you are on these lines, so it tells you where you are on these rays. Okay, sort of in some sense telling you how far you are from the origin. Okay, well, maybe you can imagine turning one of these into the other. Let's try and write down a function that would do it, which is invertible and which such that the function and its inverse are both continuous. Okay, so first of all, remember what S1 is. It's just the unit circle in the plane, so set of all points at a distance 1 from the origin. And let's define our homeomorphism from the punctured plane to the cylinder by, well, it's going to take a point x, y in the punctured plane. And, well, the idea is basically we want to sort of shrink this punctured plane to the unit circle. So everything outside the unit circle is going to get shrunk down to it, and everything inside the unit circle is going to sort of get pushed out onto it. So the way you do that is if you sort of think of xy as a vector, we're going to divide it by its length, right? So we end up with a unit vector or with a point on the unit circle, a point on S1. And then, all right, this last coordinate here is just a real number, and, well, that should sort of tell us which of these points that collapses down to a particular point on S1 is it, right? How far is it away from the origin? You might think we would just have square root of x squared plus y squared here. The only trouble with that is that we're mapping to R here, and square root of x squared plus y squared, it's always going to be positive. You can't get negative real numbers or 0. Okay, but we need to. This has to be a bijection. So there's nothing really special about logarithm here. It just happens to be a function that does what we need. So we decided to use it. This reminds you what the graph of logarithm looks like. It has a asymptote, a vertical asymptote at the negative y-axis. Well, that's not much of a... okay, anyhow, you have an idea. So The point is that its inputs are sort of positive real numbers, but its outputs are all real numbers. Okay, good. So we'll talk about the inverse of f in a moment, but let's sort of think about why f is continuous. We don't really want to attack this directly because what are open sets of S1 cross R, right? It's a product topology, a little bit of a pain. So what I want to do is sort of take this function and then follow it or compose it with just the inclusion of this cylinder into R3, right? The cylinder is contained in three-dimensional space. And one way to think of that is that the unit circle is certainly contained in R2, so this function is just going to sort of take that, well, here's what it's going to do. It's going to take the point that you put into it on S1, and it's just going to throw away the parentheses, okay? No, actually, that's not quite true. It's going to keep the parentheses. You're just going to think of it as being an R2 instead. And then it's not going to do anything to the, to the real number, okay? But now we're going to think of this as a point in R3. So now we can throw away those parentheses. And all right, so when we compose this function f with I, we get something that looks an awful lot like what we had before, okay? But it maps from the punctured plane into R3, which is basically like mapping from R2 into R3. Now, that's just the sort of function that in real analysis you learn is continuous, right, with some good old epsilon delta proofs. It may be building up through composition or addition or multiplication or square root or logarithm or whatever from some simple continuous functions to get a more complicated continuous function. Okay, so we'll take the real analyst's word for it that this is continuous. But if this one's continuous, then our original function is continuous too, because this is because of the way the subspace topology is defined, right? Remember, we're going to map from here to R3 by this function I, and well, the preimage of an open set under an inclusion function is just the intersection of that open set with your subspace. Okay, but those are exactly the sets that we've defined to be open in the subspace topology. Probably more can be said about that, but we'll leave it there for now. So, because this function is continuous by real analysis, the function f that we've defined is continuous as well. Okay, so the next question is, what's the inverse function? It should go from the cylinder back to the punctured plane. And so its input's going to be some xy on S1 and some real number z. And, okay, well, imagine we've done this function, and now we want to get back to just x and y, okay? What do we have to do? Well, we have to take our first two coordinates here and maybe multiply them by root x squared plus y squared, right? And, okay, well, what is that? This corresponds to our z here. So we have z equals log of root x squared plus y squared. And if you write that in exponential form, you get e to the z equals root x squared plus y squared. Right? So if we want to cancel these out, all we have to do is multiply the first two coordinates by e to the z. And that's exactly what we do. X times e to the z, y times e to the z. So you should check that if you sort of do f and then do f inverse, you get back the identity on the punctured plane. And similarly, if you do f inverse and then f, you get back the identity function on S1 cross R. Okay, so these are inverses of one another. And we'll do a similar sort of dance to show that this function is continuous. Again, these spaces are a little strange, but you could sort of interpose an R3 in here, right? You have the inclusion of the cylinder in R3, and then you can define a function from R3 to the punctured plane, or all the way to R2, just using the same definition. This is well defined for any point in R3. And okay, well, these expressions are certainly give a continuous function from R3 to R2. And again, because of the way the subspace topology is defined, that's also going to mean that F inverse is a continuous function from the cylinder to the punctured plane. Okay, so we have this F up here, which is a bijection, and both it and its inverse are continuous. Therefore, it's a homeomorphism, and it shows that these two spaces are homeomorphic.